Okay, let's see. So we were talking about reactions with olefins or alkenes. Either name is fine. We talked about the regio and stereoselectivity issues associated with this reaction. We talked about how when the pi bond, which is symmetric above and below the plane of the page, attacks the electrophile, you've got the option for that attack to happen from above or below, and so you get two carbocationic intermediates. So that's stereochemistry issue 1. Proton can be up or down. Second is a regio selectivity observation, which is the proton goes on the more proton goes on the less substituted carbon so that the positive charge can be on the more substituted carbon where it's more stable. Your text calls this the Markovnikov rule after the person who discovered it, but molecules don't know about rules, nor do they know about Markovnikov. The whole reason behind it is carbocation stability. So you can memorize that rule, or if you understand HOMO and LUMO and reaction mechanism, a lot of these issues just sort of fall out of the considerations. Now, you've got a planar carbocationic intermediate. LUMO of the carbocation is an empty p orbital, and it's both above and below the plane of the page as we've drawn it, and so the nucleophile can attack either from above or below. We get 4 possible stereoisomers. We talked about the difference between a syn and an anti-diastereomer, that is, do the two groups that got added to the olefin, H and Cl, end up on the same side of the original double bond or on opposite sides. There's no selectivity for that here. You can get both options, and then we talked about getting both enantiomers. Okay, anything you want to ask about that? No? Okay, so I think your text presents the next reaction almost as though it's its own thing, which is fine, but we're going to just edit what we did up there, and instead of using HCl, we're going to simply change what the electrophile is. We're going to call this alkene hydration. I don't know what the air quotes are about. They're not air quotes if they're on a paper, but years ago, 23, or I don't know how many years ago, when I was engaged to Amber, my aunt, Dinah, hosted a baby shower, or not a baby shower, that would have been funny, wouldn't it? Shotgun, yeah, bridal shower. Woo! We'll strike that from the record. In any case, yeah, bridal shower where she, and Dinah used air quotes liberally. She invited everyone to come celebrate the impending bridal whatever of Josh Price's fiancée, Amber, if that is even her name. No, I don't know. Egregious misuse of air quotes. That was an aside. I'm sorry, we're losing it, and we usually don't lose it this early. So all you got to do is replace the HCl with hydronium, and you've got alkene hydration. The stereoselectivity issues in the first step are exactly the same. You can protonate the alkene from above the page or below, and therefore the proton can end up or down. I deliberately chose deuterium so you can see that fact. If this were just a hydrogen here, you wouldn't have been able to tell. And then at the next stage, you've got a carbocation, and instead of chloride, it can just be water acting as a nucleophile to attack the carbocation. You can do so from above or below. Notice that the positive charge is still on the more substituted carbon where it's more stable. And then all you have to do is anywhere there was a chloro, you can put the water having acted as a nucleophile, now making a new carbon-carbon bond. I'm going to just abbreviate this process by leaving out the removing of the proton from that protonated alcohol. So in the end, we end up with, after that last proton transfer step, we end up with an OH on the More substituted carbon. And as with chloride, you're going to get the mixture of syn and anti-diastereomers and their respective enantiomers. So I do not recommend that you think of these two reactions as separate reactions to memorize. They're really not. They're exactly the same reaction, only the nucleophile in the second step is different. Okay? Anything you want to know about alkene hydration? This is backwards of a, oh yeah, go ahead.
Do you have any recommended tips or tricks to memorizing these?
Do I have any tips or tricks to memorizing these? First, don't. No, well, I suppose that's not helpful. So it's, as with, what's the right answer here? I would say there are some details you got to memorize and others that you shouldn't. So, or shouldn't need to. For example, I don't think it's necessary to memorize that an alkene reacts with an acid to give you a carbocationic intermediate where the proton was added from above or below, and then the conjugate base of whatever acid you used attacks the carbocation from above or from below to give you a mixture of syn and anti-products and their respective enantiomers. I wouldn't memorize that because it's annoying. But you don't need to if you understand the chemistry, because it's homo attacks lumo, and the only thing the intermediate can be is a carbocation. And the stereochemical issues come out of the fact that the pi bond is both above and below the plane of the page. So there are things you don't need to memorize if you understand the principles. There are details you will need to memorize. There were a ton of them in chapter 9. For example, nothing's going to save you from forgetting what on earth PBr3 is, or from forgetting that SOCl2 and pyridine lead to a substitution product, whereas POCl3 and pyridine lead to an elimination product without a carbocationic intermediate, whereas tosyl chloride and pyridine lead to neither substitution nor elimination products, but a stable alcohol derivative called tosylate. And you'll have to memorize that chloro doesn't come in and kick off the tosylate for some reason, even though a similar step happens in pyridine. Those are like technical details that there's no real good, at least for our purposes, first principles explanation, and it may be a detail that you just have to remember. So, to come around to the answer to your question after my 4.5 minutes of soliloquy on the subject, what I recommend for situations where you need to memorize is a couple of different approaches. One is where you take a starting material and you write what the reagent is, and you have to predict what the product is. Then another where you have a starting material and a product, but you have to fill in what the reagent was. Another where, you can see where this is going, a reagent and a product, but you have to guess what the starting material would have been. And then for super high level achievement, no, probably not. Product, and then think of, and there may be many options here for getting to the desired product. So that's, if you like flashcards, if they help you memorize things, you can totally do that. I think it's useful to be able to think about each of these reactions in these ways. How'd I do? Okay, thanks. I don't know, what were you going to say? That sucked. All right. Okay, other questions about alkene hydration? Yeah, sorry, thanks.
In a solution of hydrochloric acid with this
Oh, great question. So you can't actually generally get HCl by itself. It's always in the presence of water. So goodness, how do you get chloro to do the attacking instead of hydrogen? That is a good question. I don't know. My hand wavy response is just that Cl minus, by virtue of having a negative charge, is probably more nucleophilic than water. So that's why it probably wins when present. But that's the jazz hands explanation. I don't know that I have anything more fundamental than that. Okay, others? All right, so we are sort of sick of things that don't give you any syn versus anti-selectivity, and we may also sometimes wish to have the nucleophile end up on the less substituted carbon than the more substituted carbon. So we've got some alternative synthetic methods that will help us out. One of them, since we're talking about alkene hydration, is sort of the opposite in regioselectivity. So remember that alkene hydration gave you the Markovnikov product where the nucleophile ended up on the more substituted carbon. The reaction we're going to talk about now will actually do the opposite. It's going to put, in the end, the OH group on the less substituted carbon. And this series of reactions, it's a two-step reaction sequence, is called hydroboration oxidation. And it's going to take the same alkene starting material we've dealt with previously. The first step is to add BH3 or borane, or you can add some kind of boron reagent, but you need at least one boron-hydrogen bond. So we'll just worry about BH3. And then in a second step, you use hydrogen peroxide in water under basic conditions. And that two-step reaction sequence will give you the following product. And of course, you'll also get the enantiomer. You have to, because the alkene is a non-chiral starting material. Okay, so, but these are the only diastereomers and the only regioisomers that we observe. Would you call this a syn or an anti-diastereomer? And you would call it syn because the things that got added to the alkene, the hydrogen and the OH group, end up on the same side of the original alkene. So interesting feature number one of this reaction is we get no anti-diastereomers. And so we can say that this reaction is selective for syn addition of hydrogen and OH across the double bond. So sometimes people will call this a syn addition. Okay, the other interesting feature is that in contrast to the reaction we saw above where the OH ends up on the more substituted carbon, here the OH ends up on the less substituted carbon. So in terms of regioselectivity, this reaction is selective for the anti-Markovnikov product. That's the what. Let's talk about the how and the why. And you're going to see that the principles that apply here are exactly the same as the principles that applied above. In other words, what happens is going to be controlled by where positive charge or partial positive charge is more stable. So in that way, it's very similar to the reactions we've talked about. So let's talk mechanism. What do you know about boron? Especially, what do you know about boron that you forgot before you took the most recent exam? There's an empty p orbital that's the LUMO, right? You gonna make that mistake again? No? Okay, good. So, the empty p orbital on boron. Boron is an electrophile. It's a Lewis acid. Here is your nucleophile, and what is the HOMO of the alkene? The pi bond, right? Okay, so carbon-carbon pi bond attacks empty p orbital. How should I draw my arrow? From the pi to here, right? Okay, that is one of the arrows involved in this first step. Now what happens next is not, or rather in the same step, is probably not intuitive, but I'll show you an animation of the reaction in just a little bit, and hopefully that'll help you see what is going on. So it is true that we do form a bond between a carbon, one of the carbons involved in the pi bond, and boron. If you had to guess which of these two carbons is going to get the bond with boron? A or A? Some of you are saying A, some of you are saying B. Those are the two options. Where's C? Okay. Not C. We're going to see that B gets the bond with boron, and that would make sense if you had a carbocation intermediate, right? Because you'd have the positive charge on the more substituted carbon. But it turns out there isn't a carbocationic intermediate. That sounds confusing. So let's back up. Boron, turns out, is less electronegative than hydrogen. And what that means is BH3 sort of is a carrier of a nucleophilic hydrogen. The other thing about boron is if you form a bond to it, it's now got four things and should have a negative formal charge. And that negative formal charge is felt mostly on these hydrogens. So what happens in the same step as we're making a new carbon-boron bond is that we're actually going to deliver H- to the other carbon in the same step. Let me sort of draw for you what this transition state looks like. We're going to have a dotted line between the two carbons A and B because the pi bond is breaking. Okay, we're going to have a dotted line here between carbon B and boron. Oops. And in that transition state, there's going to be a buildup of partial negative charge on the hydrogen. The reason for this is, as I said, if you make a fourth bond to boron, boron will have a negative formal charge, but by virtue of the fact that boron's less electronegative than hydrogen, most of that negative charge is actually going to be out on the hydrogens. And so the last line we need to draw is, sorry, I meant to do this differently. The last line we need to draw is the dotted line between the nucleophilic hydrogen and the other atom of the double bond. And then I'm also going to fill in the methyl group and the deuterium. So this is what the transition state looks like. There's a lot of things going on at once. in this transition state, we are forming the new bond between boron and carbon B. That's indicated by this arrow. At the same time, we are forming a new bond between hydrogen and carbon A, taking the 2 electrons from the boron-hydrogen bond and delivering them with the hydrogen to carbon A. All right, so this first transition state for this reaction tells you why this is a syn addition. And the reason for that is you can basically envision the boron hydrogen bond sort of sitting down on the face of the alkene. And in a 4-membered ring, there's simply not enough space for boron to deliver the hydrogen to the bottom side. Both reagents, both hydrogen and boron, get delivered to the same side of the alkene. The regioselectivity issue, or why we form the bond between the less substituted carbon and boron, is that bond, boron-carbon bond, is more formed in the transition state than the carbon-hydrogen bond. And I've tried to indicate that by showing this distance as being a little bit less than this distance. In the transition state, the carbon-boron sigma bond is more formed than the carbon-hydrogen sigma bond. What that would mean then is that as these electrons are pulled over to form a new bond between carbon and boron, there's a buildup of partial positive charge in the transition state, and we prefer it to be on the more substituted carbon where it's more stable. All right, so the intermediate you get after that addition process will have the hydrogen on the more substituted carbon, the boron on the less substituted carbon, and the hydrogen and the boron must be delivered to the same side of the original alkene. And then you're also going to get the other enantiomer. Still, it's a syn diastereomer. We still have syn addition of boron and hydrogen across the double bond. Okay? Yes?
So why is it that you have a partial positive right there on the boron, but it's not on the transition state? I believe you might have covered that. Would you mind going back?
Here I showed you that boron is less electronegative than hydrogen, so that boron is the electrophilic part of this molecule, and as I make a new bond with boron, hydrogen ends up getting more nucleophilic. Okay, I didn't draw that here. I probably could have, but the most important feature of the transition state is, first, all of this happens in the same concerted step, so it's syn addition. Second, in the transition state, the carbon-boron sigma bond is formed to a greater extent than the carbon-hydrogen bond. That requires a buildup of positive charge on the more substituted carbon where it's more stable, and that controls the regioselectivity. Okay, what else? Yeah?
I was thinking that the boron would go to the B because it was bigger. Does that have anything to do with it, or is it?
Okay, can the boron go to the less substituted carbon because of sterics? Yes, although in BH3, the rest of boron, I mean, it is still pretty small. So, but there are hydroboration reagents which have much larger groups here, to other alkyl groups on the boron. And so, yeah, you can invoke sterics as an explanation for why boron ends up on the less substituted carbon, and that will give you the right answer too. A good rule of thumb in organic chemistry that we often repeat jokingly to each other is there are two explanations for everything. One of them is sterics and the other is electronics, meaning like where the positive charge is more stable. So if it's not sterics, then it's electronics, which usually means hyperconjugation. Don't worry about that. I don't know why I'm telling you esoteric parts of OChem nerd culture, but that was one of them. Okay, I want to show you an animation of a hydroboration reaction, if I can see one. Alkene addition, hydroboration. Okay, so this is going to be addition of BH3 to the pi bond in 1-butene. No, not going to let us zoom in. You can see the pi bond, you can see the boron, all right? We're going to watch this distance between carbon and boron as the reaction proceeds. Sure, whatever. You see that distance shrinking. At the same time, do you see the bond between, you see the distance between carbon and between the two carbons A and B increasing because the pi bond is breaking. You can sort of see the boron rehybridizing and going somewhat sp2 hybridized, or sorry, sp3 hybridized as it gets more trigonal planar. We're not to the transition state yet, but do you see that as we approach it, the carbon-boron bond or distance is quite a bit closer than the carbon-hydrogen distance. So as this approach is happening, there is a buildup of partial positive charge on the more substituted carbon where it's more stable. As we continue onward, we're going to get to the transition state. What? So it's still in development, apparently. And you have to press play and then see the transition state? No, it thinks the transition state's at the beginning, which it isn't, but. All right, I'll press pause and we'll just drag this along. As dotted lines start to happen, that'll be basically the transition state. See that? We're forming a new bond between carbon and boron at the same time as we're breaking the bond between the two carbons and at the same time as we make a bond with the hydrogen. So that's just a direct handoff of the hydrogen. And the regioselectivity, as I said, is governed by the fact that boron interacts preferentially with the less substituted carbon so that the buildup of positive charge can be on the more substituted carbon. All right. Anything else you want to see there?
So the hydrogen attaches before the boron attaches? Or is it just
I noticed that in this simulation. Now I can't somehow adjust it so we can see everything. So maybe we just reset everything. No, still not. Okay. It looks like at the beginning, boron gets closer. And then I noticed the same thing you did, which is after the hydrogen gets delivered, there's sort of this spring backwards so that's probably an interesting feature of the reaction, but probably not one that's important, I guess. Yeah. Okay. If you find that this organic reactions animations app muddies the water and makes your life more difficult, you can send me an email and tell me that I shouldn't do that in class, and then maybe I will listen to you. Whoa. What's going on there? Okay. Right, so we've only done step 1 here, hydroboration. That is going to explain the syn addition and the fact that boron gets on the less substituted carbon. Now, the second step is understood and the mechanism is known, but I don't really care that you know it. If you want to know it, you can come talk to me, we'll work through it and I'll show it to you. It's not that hard, but it's also not that useful to know, and so I'm going to skip it. This is going to be sort of magic Lego chemistry. These conditions are oxidation conditions. They literally replace the carbon-boron bond with a carbon-oxygen bond, and they do so without changing stereochemistry where the boron is. And, you know, as I said, this is going to look like magic chemistry, and this may be one of the details you have to memorize because I haven't explained why or how it happens. That stuff is known, but it's not that useful to know, at least at this stage. So I want you to know the mechanistic details of this first step, because that's going to explain why we get the anti-Markovnikov regioselectivity and why we get the syn addition product, and that's all sort of explained by this transition state. But I don't really care that you know how this last step works, where the boron gets replaced by an OH group. Yeah?
It's just a substitution reaction, right?
Is it just a substitution reaction? Not on the carbon itself, the carbon B to which the boron's bonded. That's actually not involved in the reaction. It can't be, or you would get inversion of configuration. Yeah. All right. Anything else? I feel like I'm holding out on you. I really would like to show you that explanation, but I have before, and then I found that it was too painful for everyone involved, so we just won't. All right, others? All right, now notice what you have the ability to do in terms of a synthesis. If you take this molecule 1-butene, you can do regular acid-catalyzed hydration of an alkene to give you the Markovnikov product, where the hydrogen ends up on the less substituted carbon. We get a carbocationic intermediate, and the OH ends up on the more substituted carbon. Or you can use hydroboration oxidation conditions to give you the alternative product, in which you have the OH on the less substituted carbon A, and the hydrogen gets delivered to the more substituted carbon B. So we have regiochemical versatility here. That's useful in synthesis if you're making molecules for various purposes, to be able to at will switch which carbon has the oxygen from the same starting material. That's really quite helpful, quite useful. There's a thing in OChem, again, another issue of OChem nerd culture, called diversity-oriented synthesis. And this is taking the same starting material and doing different things with it based on a different set of reactions. If you can take the same starting material and turn it into a large number of different things, that is useful for generating a lot of new and possible drug candidates. But that's all I really want to say about that. So, anything else? Yeah?
So just to be clear, so with hydroboration then, so the OH does not go to, it doesn't say to the less substituted carbon, or it can move around?
The OH in hydroboration oxidation does end up on the less substituted carbon, yes.
Okay.
Go ahead.
Oh, sorry. So then on that bottom picture there, I maybe just missed something, but it looks like the OH on the bottom is on the, oh sorry, on the top is on the more substituted carbon?
It is, but that's alkene hydration conditions, yeah.
Okay. Sorry.
No, that's fine. Excuse me. Oh, I'm needing to clear my throat so much today. Okay. Others? All right. So we have 2 more reactions in chapter 10 to go. Fortunately, the last 2 are basically the same reaction. And in any case, alkene hydration and hydrohalogenation are basically the same reaction anyway. So even though you think there's 5 reactions in this chapter, there's maybe 3. Okay, next is called alkene halogenation. And I guess we can continue to use the same starting material. It's helpful to stick with that pattern. Halogenation is addition of Br2 or Cl2 across the double bond. So let's use Br2, but we could just as easily use Cl2. The two things that are going to get added to carbons A and B respectively are both bromine. So there are no regioselectivity issues to deal with here for this reaction. Both carbons end up with a bromine, so it really doesn't matter which one gets the bromine first. The second feature is that the reaction is selective for anti-addition. That is, the bromines are going to end up on opposite sides. Always. Anti-addition of bromines. As before, because the alkene is a non-chiral starting material, you should expect to get both possible enantiomers. But unlike the alkene hydration or the alkene hydrohalogenation, you don't get you don't get any of the syn diastereomer. Okay? So as we saw before, for hydroboration oxidation, where we got exclusively syn addition, we saw that there was no carbocationic intermediate. So there was no option for the second thing to be delivered from both above or below a planar carbocation. And so you would predict the same thing here, that there can be no carbocationic intermediate. Otherwise, we wouldn't have the selectivity for the anti-product, or where the bromines are trans to each other. All right, so the mechanism here is, I think it's kind of cool. I doubt you will feel that way. But as you've no doubt seen, organic chemistry doesn't care how you feel about it, so we'll just proceed through it and show you what reality is. Okay, so as before, nucleophile attacks electrophile, HOMO attacks LUMO. The HOMO of the nucleophile is the carbon-carbon pi bond. The LUMO of the electrophile, the only thing it can be is the sigma star between the two bromines. But we realize at the same time that bromine has non-bonding lone pairs on it, which themselves are nucleophilic. So we attack, we have the pi electrons attack bromine, and that breaks the Br-Br sigma bond. And if we stop there, you would predict some kind of intermediate that would look like this, where you would have formed the carbon bromine bond here, and you would have predicted that you'd have a carbocation on the more substituted carbon. If that happened, the bromine has a lone pair and it's quite close, it would just snap closed to form a three-membered ring. And there's evidence that actually you don't even get to this intermediate. Instead, at the same time as we're making a new carbon-bromine bond, lone pairs attack the other carbon. I'm trying to figure out how to show this. Some of you may be wondering, do I always have to show the arrow from the lone pairs going to carbon B and the arrow from the pi bond looking like it's originating from carbon A? No, you actually can't tell which one happens first. They both happen at the same time. So I could just as easily have drawn the mechanism with the arrows going the other way. But the intermediate that we get now has a bromine bonded to two carbons, A and B. And now you may be having flashbacks to your first exam where I showed you an intermediate like this and you had to calculate the formal charge on the boron, which wasn't 3. 7, no. How many electrons does bromine usually have? 7 currently owns 6, that's plus. Okay? I told you there was no carbocationic intermediate, and that is true because the positive charge is, formal charge is on the boron. So what I told you is true from a certain point of view. Yeah, go ahead.
How does the steric string or able string it's not work on that? Like, why does it form a 3-membered ring so easily?
Why does it form a 3-membered ring so easily? 3-membered rings are highly strained. You have to remember about boron, it's actually huge. It's larger, and so what you're really looking at almost is a boron atom sitting down on top of a pi bond. Did I say, oh my word, both. Can we have things not start with the same letter? Bromine. Bromine is large and it's sitting down on the pi bond. You're right to predict that these bromine carbon bonds are both long, and they are. And because of that, the strain issue isn't quite as bad. I'm going to see, do we have alkene addition? No, they don't have that. I wonder if we can draw that intermediate in Spartan and just sort of see what happens. That's pretty. Sort of looks like an epoxide. But you can see that relative to the size of the carbon, length of the carbon-carbon bonds, that carbon-boron bond is quite a bit longer. So there's a lot less ring strain because the 2 carbons A and B that are bonded to the boron, bromine, man, how many times am I going to do that? The 2 carbons that are bonded to the bromine are still basically sp2 hybridized, so there's way less ring strain going on here. Let's see if we can look at space filling. Yeah, I mean, it literally looks like that's just a regular alkene, only the bromine is evenly shared between the 2 carbons. All right. Then, yes?
Is there a reason why the bromine attacks the B carbon, not the A carbon, or does it matter?
No, the question is, I've shown it as though we're forming the bond between A and bromine first, and then lone pairs on bromine attack B. It's just as fine and perfectly legitimate to do it this way. And in fact, you can't tell because in the end, you get the same thing either way. Yeah. All right. So we're not quite done. This intermediate is called a bromonium ion. And it's the ium is sort of what we do, right? You've heard of ammonium or oxonium, sort of what we, when we're talking about an ion that has a positive charge on bromine or an oxygen or a nitrogen. This is sort of the language we use. Then in the second step, Br minus, which was the leaving group in our first step, will come in, and this now is basically the same thing you learned for epoxide opening. You're going to open in an SN2 fashion from the backside of the bromonium ion. That's going to give you selectivity for the anti-product. Now, as I said, it really doesn't matter which carbon gets attacked because both of them are getting the bromine in the end. I'm going to draw this as though it's basically the same thing as opening up of a protonated epoxide. Do you remember how we said that a protonated epoxide opening is very SN1-like in the sense that there's a buildup of partial positive charge on the more substituted carbon where it's more stable. I'm going to draw the Br minus attacking the more substituted carbon, and you can't. There's no way you can do an experiment to verify that that's the case because both carbons end up with bromine. But I'll show you in just a little bit a variation on this reaction where it looks like there's pretty good evidence that the thing that acts as a nucleophile in the second step does attack the more substituted carbon. But when you do that, I don't need this arrow here. You're just going to go up top, and that will give you the two products. I should have, I suppose, drawn the other stereoisomer, the other enantiomer for the bromonium ion intermediate. Because the starting material is not chiral, you can't have selectivity for bromine sitting down on the alkene from above or below. So you get both of these enantiomers. They both are opened up by Br minus in the second step to give you that product. Okay? We could have done the same thing with Cl minus, and it works too. I want to say a little bit about structural patterns and recognizing them, because this is actually, this 1,2 dibromide situation is really actually kind of useful from a synthesis point of view. Before we do that, any questions about the reaction mechanism? Yes?
So just want to make sure I'm understanding the things right. The one where the carbon-bromine bonds are wedges, that will turn into the one where the
Sure. Let's see. That would give you, I guess, this one? Yeah.
okay. So it does switch the stereochemistry.
Yeah. Yes, the opening is SN2 backside attack with inversion of configuration, just like we saw in epoxide opening. All right, this product has a bromine on 2 adjacent atoms. You could call the product a 1,2 dibromide, and that would work. Another word we use for 1,2 substitution is vicinal. That's from either the Greek or the Latin. Spanish speakers, the word for neighbor is vicino, so it's they are on neighboring carbons. Vicinal dibromides are useful because you can use them in a synthesis. So for example, I could start with this alkene. I could use bromination to make the vicinal dibromide. And now we're going to circle back to something you saw in your study guide and practice exam that we didn't talk about. The vicinal dibromide has 2 sets of, it's spring-loaded for 2 sets of elimination reactions. And so I'll draw this mechanism later, but you can take a very strong base like NH2 minus, and if you use 2 moles of NH2 minus for every mole of starting material, you can actually convert that vicinal dibromide into an alkyne. Play around with that and see if you can figure out how to get there. And we'll talk more about what to do after this later.